Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on this course on control systems. So in the previous lecture we started looking at something which was kind of like a shift from whatever we've been doing thus far, in the sense that we started looking at the so-called frequency response of linear time invariant systems. Of course, we've done a bit of groundwork initially when we introduced Laplace transforms, if you recall, right at the beginning towards the introductory lectures, the first few lectures, where we actually saw what this transfer function actually implies, right. So we saw that if you give an exponential e to the at as an input to a system, and if the system's transfer function is given by gs, then in order to get the output, all that you need to do is you need to substitute s is equal to a, yeah, and you will get basically this. So suppose you give e to the at to a system which is captured by a transfer function given by gs. So this is a hybrid notation, please read it in such a way, yeah. And basically the output, yeah, this output y of t turns out to be this is g of a e to the at. In fact, we give it a name, we call it an eigenfunction. Doesn't matter, we really don't need to bother with that. It's after all a name, right. And now in the previous lecture we've actually seen this at work, yeah. We have seen when a is equal to j omega, what the consequences of this result are. Actually I could have just applied this result instead of going about it in that laborious process of taking the transfer functions, partial fraction expansions, and then finding out the residues and then putting them together. In fact, I'm still not sure if I didn't err in the signs in any place, but it doesn't matter, you get the essential idea. Even if there's a mistake in the sign, you can take care of that. Right. So now in this lecture we shall focus our attention to some specific kinds of transfer functions. And why do we do that? Yeah, because remember that there are only certain different types of transfer functions that we've seen here, yeah, and they have some component blocks. So we have seen only rational transfer functions where the transfer function is given by the ratio of two polynomials, one in the numerator whose roots were the zeros of the transfer function, the other in the denominator whose roots were the poles of the so-called transfer function, right. So we can factorize these polynomials in certain ways, and therefore this gives rise to the question, if we know that each of those constituent factors have a certain kind of behavior with respect to omega, okay, if they have a certain kind of dependence on omega, then can we not sum together or aggregate these effects when we put them together in the polynomial? And this is where what gives rise to the first important idea, yeah. Now just to refresh your memory from what we did in the last lecture, we did see that if you have this g of j omega, you can write this as m omega times e to the j phi of omega. Of course you can also write it in the polar form as, yeah, that's just an alternate representation of the same thing, yeah, it's one and the same thing. So this is how we generally can represent any complex number for that matter. It just so happens that this depends on omega, yeah, if you forget about the omega dependence, it's just a representation of a complex number after all, right. So now we saw that when you have this sort of a transfer function, and if you give it an input like e to the j omega t, right, then we see that this gets amplified by or attenuated by m omega, and so two things, and phase shifted by phi omega. So those are the two things that happen to signals like these, all right. Okay, so now that we have seen this, let us try and understand what form this m omega and this phi omega takes. Okay. So of course, as with any complex number, we can split up this gj omega into its real part of gj omega plus the imaginary part of gj omega, and then we know that the magnitude function m omega, which is an even function as we have seen, yeah, it's going to be nothing but the square root of the real part of g. Of course, I am omitting this j omega for brevity, but you can understand that it is there, yeah, and this phi of omega, which is equal to minus phi of minus omega, because it is an odd function, is given by, of course, tan inverse of imaginary part of g upon real part of g, right. So now notice that we said that there is a certain form of this this transfer function, it is a rational function after all, right. So then what I wonder, do we know about products, yeah, that allows us to treat them like sums? The immediate idea that comes to mind is something like logarithms, right. So if you have two numbers m and n, then you know that the log of the product of two numbers is equal to the sum of the individual logs, of course with the same base, yeah. So that is a quick idea. So for example, if you have a polynomial given by this s plus p2 dot 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 till s plus pn, and if you take its log, yeah, suppose these are all, we are taking the magnitudes, if you take the log, then this is nothing but the sum of the s plus pi I going from 1 through n, yeah. We know this with respect to some common base. In general, the base is 10. Of course, in calculus we take the base e, yeah. So what idea, I wonder, does this give us? I mean, how does this help us through with our procedure? Okay, let's try to take a look at this. Look at this. How have we represented this transfer function? Focus on this, yeah. So now you notice that if we take the log of this with the base 10, let us say, of g of j omega, yeah, I can immediately separate it out into two parts such that the real part is going to give me the log of the magnitude function, and the imaginary part, of course with some scaling, subject to some scaling, I get j phi omega and maybe the log of e to the base 10, yeah, but this is after all a constant, a natural constant, some value which I know, some gamma, some real valued gamma, some function or some real valued number, not function, some real valued number. So this is not a function. So indeed we see that when we take the log of this, something beautiful happens. Not only, yeah, not only am I now able to, if I can split up the components of this m omega in the product form as we might be able to do in case of a polynomial, not only does this allow me to break this up, but also this overall transfer function gets split up into its real part and its imaginary part, where the real part is exclusively the magnitude function and the imaginary part is exclusively the phase function. Now let us look at this particular example once again, this particular kind of a complex variable, right. Suppose you have a transfer function given by s plus z1 into s plus z2 divided by s plus p1 times s plus p2 times s plus p3. Yeah. Now you substitute this at j omega, so g of j omega, and you take its log. Yeah. Then by the preceding expression I know, right, that this can be written in this form. So this is nothing but log to the base m omega plus some constant times, yeah, this constant times, yeah. Of course there's a j, so that's a imaginary part, some constant times phi omega. Now what I wonder is the form of this m omega. Look, I know that this g j omega can be written as j omega plus z1, individual mods if I take, yeah, that's again complex arithmetic, nothing, no big deal here. If you want to take the mod of this entire g, then you better take the mod of individual blocks. You can always do that for complex numbers. So this is this is going to be again j omega plus p1 times j omega plus p2 times j omega plus p3. Yeah. Now what do I know about these individual blocks? If these are real numbers, suppose z1, z2, p1, p2, p3 are real numbers, then what do I know about this? Each of these individual blocks, I know what their real part and their imaginary parts are. So this is nothing but omega squared plus z1 squared under root times omega squared plus z2 squared under root divided by, and you get the idea. Right. So now if I take the log of this, yeah, so remember what is this? This is nothing but the log to the base 10 of m omega. Yeah, if I take the log of this, then that is equal to the log of this, and that is equal to the log of this. But now I know how to take the log of products and quotients. So I add the log of this plus the log of this and subtract the logs of the three individual terms here. Yeah. Okay, that's probably a stray plus sign remaining over there. Yeah. So then I know the log to the base 10 of m omega is equal to log of summation square root omega squared plus zi squared minus summation log of square root omega squared plus pj squared, j going from 1 through n, I going from 1 through m. Suppose there are m zeros and n poles, this is the general expression. Yeah, and this is beautiful because now this gives me a handle on how to plot this m omega. Of course, you might say not m omega really, but the log of m omega, and that is precisely the reason that we give rise to this plot called Bode plot, not we, but actually H.W. Bode. Yeah, that is the name of the scientist who proposed this Bode plot, right? It's named after him. So that is what the idea behind this Bode plot is. Yeah, because these are all, after all, polynomials which can be factored into simpler terms. So why not look at the magnitude functions of those simpler terms and then just add them or subtract them? That is the idea. Of course, the price that comes that you have to pay is that you have to look at only the log of these, but that's not such a big deal. There are things like semi-log and log graph papers. You may not be very familiar with these. You may have only seen those linear kind of graph papers. Yeah, but there do exist these graph papers. The beautiful thing about them is, in the semi-log case, you have the x-axis, the independent axis labeled in the logarithmic scale. What that means is, that suppose you have 1 here, you will have 2 over here, and you will have 10 over here, and almost exactly the equidistant. So this is called 1 decade, because there is a multiplication of 10, and exactly the same distance ahead, you will have 100 over here, and you will have this 20 sitting pretty almost halfway through. Yeah, but that is all about the log scale after all, right? It is not a big surprise, no, because you notice that log 1 is 0, log 2 is 0.3, of course we are talking about log with respect to base 10, log 10 is 1, log 100 is after all 2. So if you take the log of these, you know, if you pass them through log, then after all this is going to be 0, this is going to be 1, this is going to be 2, and so it makes sense that they are equispaced. Yeah, that is what the log scale is. So you might wonder, what other benefit does this have? The benefit of this log scale is that in a single graph paper, you might cover a very wide range of independent variables. Yeah, of course this might not give you very precise, in fact as you get larger and larger, as you go more to the right, the precision decreases. But we will see in the context of this Bode plot, that really is not that significant, okay. So for example, there is a very high resolution as you go from 0.1 to 1, there is a little less resolution as you go from 1 to 10, but there is even worse resolution as you go from 10 to 100, and forget about from 10 to the power 5 to 10 to the power 6. Yeah, within that same space you have to fit in 10 to the power 5 to 10 to the power 6. Yeah, so you can imagine that the resolution isn't going to be as good. It's going to be as if like somebody is squeezing it. Yeah, as you go higher and higher, it's being squeezed in. Too many frequencies are being squeezed in within a small space. So that is the penalty you pay. But the good thing is that if you don't really care about that precision, but if you want to get a picture over a wide range of frequencies, which we often do in case of system identification, then this log-log graph paper and this log variation of this independent variable is actually a blessing. Okay. Now I want you to quickly note another thing. Not only do these magnitudes when taken through the log get added, but what happens to the phase? Now remember, I hope you remember that when you have these two complex numbers z1 and z2, and if you take their product, then you see this argument function also behaves like the log function, no, in itself. That is equal to argument of z1 plus argument of z2, right. So it turns out that this splitting is not only beautiful because it splits up this gj omega into its real and imaginary part, where the real part is the magnitude function and the imaginary part is a scaled version of the phase function, but also whatever you do to individual blocks in so far as their magnitudes are concerned, yeah, you do the exact same thing to the phase functions. So what I am saying by that is, so for example here, you add together all the magnitude functions after passing them through the logarithm, all the magnitude functions of the blocks in the numerator, add together all the magnitude functions after passing them through log in the denominator, and take their difference. But what do you do about products and quotients in terms of arguments? So for example, you have z1, z2, or let me not take z1, z2, let me take the actual function itself. So you have j omega plus z1, this is a complex number, you have j omega plus z2, and then you have j omega plus p1 times j omega plus p2 times j omega plus p3. Now if you want to take the argument of this complex number, what you do is exactly the same. You take these individual components, yeah. So the first term's individual component is tan inverse omega by z1 plus tan inverse, yeah, so let me just split it up here, tan inverse omega by z2 minus tan inverse omega by p1 minus tan inverse omega by p2 minus tan inverse omega by p3. In other words, you take the individual arguments of the ones in the numerator, add them together, take the individual arguments in the denominator, add them together and take the difference, yeah. But that is exactly what we did with the magnitudes. So that is the beauty of this. You see, in taking this logarithm, we get so many advantages. One is, of course, we are fitting it over a wider range of omega. Two, we have now clearly and cleanly separated the magnitude and the phase part as the real part and the imaginary part of this logarithm of gj omega. And three, whatsoever we do unto this m omega, yeah, in the sense that whatsoever we do unto these constituent blocks of m omega, that we do unto every single constituent block in obtaining phi omega as well, right. You find out the individual phases of those blocks or those individual blocks, add them together if they are in product, subtract them if they are quotiented. You do the same with the log of the magnitudes as well, yeah. So the same type of operation, and that is in a sense a Bode plot. So a typical Bode plot would look something like this, where it's a semi-log graph paper, that's why you have linear scale on the y-axis. So this is basically going to be m omega 20 times log m omega, and here is another point that needs to be made, yeah. Already we have seen that this imaginary part of this function is a scaled version, not exactly equal to phi, but some scaled version of phi, some gamma times, whether it's log e to the 10, e to the base 10, yeah. But here also we see that although this appeared clean and clear as just the logarithm of m omega, we are still multiplying it by 20, and you might wonder why. Now, of course, the easy answer is that it's a convention, yeah. So this is an omega axis, this is of course the log axis. So you will have some point like here 0.1, then you will have 1, and equidistant from it you will have 10, equidistant from it you will have 100, equidistant from it you will have 1000, and so on and so forth. So yeah, so on a semi-log graph paper whose x-axis is in the logarithmic scale, yeah, and the y-axis is in the linear scale, we plot this 20 times the log of m omega and just phi omega. So now you might ask, why is this 20? First, I will explain it in two parts. So I am going to split up, and you might think I am doing some funny rubbish here. I am going to split this up into 2 into 10, and I am going to explain why each of these two terms come in. So remember that 10, why does this 10 come in? If you have, for example, let us say you have weight in kilograms, you are trying to measure some weight in kilograms, okay, and if the quantity is very small, right, if the quantity is, let us say, some 5 grams, then you want to specify it as weight in kilograms, you will have to say 0.005 kilograms. And then if you are labeling your axis those units, yeah, in terms of kilograms, 0.005 is very badly scaled. I mean, that plot does not reveal much. It will, for all practical purposes, look like it is almost close to 0. Now on the other hand, if you plot your axis and take the unit to be grams, then you will have 5, okay, and 5 is distinctly away from 0. So it's, think about a graph paper that you've been given, yeah, and you're plotting the weight of different quantities, and the weights are all in grams, like 5 grams, 10 grams, 20 grams, 15 grams, things like that, yeah, and somehow you have chosen the unit to be kilograms, right. So then you would plot all of these very close to 0, and to a user who sees this plot will say, I am not able to make out anything out of this. Why don't you go back and plot in grams? That is exactly the principle here. So it turns out that the unit of this log thing, yeah, this 2 log some m, yeah, this is given in bells. So this was in Bell Labs. This was called Bell, so that was the unit. But those units may not be sufficient for the systems that we are considering, in the sense that our systems gains are way too small compared to 1 bell. So that is why this unit called decibel. So there are two conventions, some people write it as dB with a small b, some people write it as big B, yeah, to denote the same thing. So I don't mind either notation, and I sometimes use one or the other, but if you are using in the same document, be sure to maintain consistency, either use small b or use big B throughout. Yeah. So that is why, because this gain, this amplification isn't really big enough when measured in terms of bell, yeah, that is why you go for this unit decibel, and therefore what you do is you multiply it by 10, just like if you want to get this kilogram to gram, you have to multiply by 1000. If you want to measure small units in kilograms, you are calling it 0.005, now you want to measure it in grams, so you multiply it by 1000. So similarly deci, you know, milli, centi, deci, yeah, then there was deca, then heka, and so on and so forth, right. So this deci is just 1/10 lower than this bell, so it is a 1/10, so therefore you multiply it by 10 in order to account for that. So that takes care of this factor of 10. Now you might wonder what brings this factor of 2, yeah. Well, it is simply a pragmatic choice for the simple reason that in most of the systems that were being dealt with in the Bell labs in those days, they were electrical systems. So they were actually looking at powered amplification, okay, powered amplification. But you are not measuring power directly, no. What are you measuring? You are measuring voltage. So remember, power is proportional to the square of the voltage, right. So therefore the measured variable was voltage, but the power was proportional to square of the voltage. So therefore log of P is proportional to twice log of V, yeah. So that brings this factor of 2, okay. So therefore putting these two pieces together, one, this 2 comes in because people are used to this idea of power amplification, so they call it 2, and this 10 comes in because decibel was deemed to be the appropriate unit for identifying the gain of the system at different frequencies. So that is why you multiply by 20 overall. So that is what brings this factor of 20, okay. So on a plot such as this, what we now want to do is, we want to see how this m omega, or this 20 log to the base 10 m omega, varies with omega and the phi varies with omega. What will that help us to do? Suppose I have been able to plot this graph like this and this graph somehow like this. How will it help me? It will help me in the sense that if I now know that there is a signal which I have cooked up by combining components of frequency such as this and this and this, so if it is a sum of 3 frequency components, yeah, then I know that this component is going to be amplified by a factor such as this component is going to be amplified by a factor such as this, and this by a factor such as this. So I can just as well amplify these individual units, because it is a linear system, as I said. You can take the individual amplified versions of those signals, phase shifted by so much phase here and so much phase here, yeah. So you know what the output due to this particular input is, what the output due to this particular input is, and what the output due to this particular input is, right. So therefore you sum together those 3 outputs and you get your overall output. Because it is a linear time invariant system, it makes all the sense to do all of this, and we can obtain this output, right. So that is what the benefit of being able to draw this so called Bode plot is. So this, we shall now look at some special kind of blocks, the building blocks for a Bode plot. Now recall that for the root locus case, we were very insistent that for root locus, we represented a transfer function in this form, where we had this k and then we had this product of s plus zi divided by the product of s plus pj. So j running from 1 through n, I running from 1 through m. Of course, these zi's and the pj's need not all be distinct. So there could be repetitions of zi's, there could be repetitions of pj's, okay. So this was the form in which we wanted our transfer function to be before we embarked on this root locus, and which is what precisely led us to conclude that if you have right half plane zeros, recall, yeah, then you must look at the complementary root locus, yeah, because ideally a right half plane, a non-minimum phase transfer function such as that would be given by z minus s form. So when you invert the sign of that, you better invert the sign of the gain as well, and then start looking at the complementary root locus, yeah. So that was all because we wanted this transfer function in this particular form. Now it turns out that for Bode plot also we want our transfer function to be massaged in a particular form, just that it is not going to be the same form that worked for the root locus. I mean, you can always do this, but we prefer our Bode plots, for our Bode plots to set up our transfer function in a particular form. So what is that particular form? Here is how we will write this transfer function. So our transfer function will have this gain k, but hang on, this is not going to be all. So then you are going to have I is equal to 1 to m1 1 plus tau I j tau omega, yeah, j tau I omega, yeah. Let us call this tau zi, because these are zeros, okay. Then you will also have terms like I is equal to 1 to m2, and these are the second order terms. Now remember, we do not want to factorize like we did for a root locus. We could factorize the root locus by complex factors as well, but in case of Bode plots we do not want to get into this complex factor business. We only want to stay over the real field. So then this will give us terms like j omega over omega n squared. So this omega n also has to be indexed, yeah. All these indices sometimes make it appear very messy, but they do help us. So omega n zi squared plus 2j zeta zi, yeah, all indexed by this zi, and then we have omega upon omega n zi, yeah, and plus 1. This is all there is to the numerator. Then you can also have terms like j omega to the power r, yeah. So the r could be positive or negative, so you can have poles or zeros at the origin, yeah, divided by, again similar type of terms, only that the z's will be replaced by p's. So let me call this I varying from 1 to n1, 1 plus j tau pi omega times pi I ranging from 1 through n2, and once again we have the same type of term j omega, sorry, this is j omega squared I think, so I put that square sign mistakenly inside. So j omega upon omega n pi now, yeah, omega n pi squared plus 2j zeta pi omega over omega n pi plus 1, yeah. So this is the typical form in which, of course, you can also consider some irrational parts like e to the j omega t, but we will consider them later separately, yeah. For now we will just bother ourselves with rational transfer functions such as this. So you notice there is one significant difference between the way it was represented for a root locus and the way we are now setting it up for a Bode plot, yeah. And the difference is that now if you substitute omega is equal to 0 here, this k is basically nothing but the DC gain. On the other hand, here if you wanted to find the DC gain, it would be basically this k, so the DC gain would be equal to k product of zi upon product of pj, right. So this k and this k are definitely not the same, so we are setting it up in a different fashion. Please be mindful of this. So every single tool that you use has some typical nuances, has some typical ways of dealing with it. So the first thing that we do is, when we are dealing with root locus, as opposed to that, yeah, when we are dealing with root locus we set it up in this fashion, but when we are dealing with Bode plots, this is how we prefer to set up our transfer function, and pull out this k as a DC gain. So now of course let us define, so this r is basically any integer, it could be positive or negative, and this k, then this tau pi, tau zi, then this omega n pi, omega n zi. What else have we got? Yeah, we've got zeta zi, zeta pi. All of these are real numbers, and not just real numbers, but they all have to be positive as well. Yeah, of course the zeros need not be all positive, but at least the poles, yeah, these factors, the pi's, they must be positive. But anyway, we'll, for now let's say they are real. So we'll implicitly assume, as we've already said earlier, it doesn't make sense to draw a Bode plot for an unstable system. So we'll implicitly assume that whenever we are talking about Bode plots, the system is at least stable, right? So now the hope is that let us now categorize this or break this down. So what are the different kinds of blocks that we have? One block is of course this k here. The second block is of course this j omega to the power r here. The third kind of block is 1 plus j omega tau. So I'm dropping the zi and pi and all of that, and this is of course again to the power plus minus 1. If we know how it behaves for plus minus 1, we can just keep adding more and more such blocks to get plus minus r. In fact, the same thing holds for this j omega to the r as well. Yeah, so we will just see for r is equal to plus minus 1. So we will see this for r is equal to plus minus 1, and if you have greater than that plus minus 1, if you have 2, 3, 4, 5, you can just keep adding more of them, as we've seen, right? The magnitude function is nothing but the addition of each individual component. So that's a third type of block, and finally this is the last type of block, which is this j omega upon omega n squared plus 2 zeta j omega upon omega n plus 1. Yeah, this also of course can be raised to plus minus 1, right. So the hope is we want to answer the question, what do the m omega and phi omega look like for these elementary building blocks. Why are we interested in answering this question? As I have already said, if we have an answer to this question, this so-called starred question here, then it turns out that given any rational transfer function, all that we need to do is, on the semi-log graph paper, we just need to add up terms or plots like these. So if we can characterize what plots for these individual blocks look like, yeah, then we can actually plot for any given transfer function, any arbitrary rational transfer function given to us. If we know how to sketch the Bode plot for each of these, by that Bode plot I mean not just the magnitude plot but the phase plot as well. So that's why I have written both the magnitude and the phase. So if we know how to plot this in a graph paper, then we are done. That is essentially all there is to basically sketching a Bode plot. Later on we shall see that there are a lot of other concepts that are involved that emerge from this frequency domain. So you might have heard of several terms like bandwidth, like resonant frequency, and we've been talking about this non-minimum phase. All of these things, yeah, will make a lot of sense once we understand Bode plot. At this point, let me remark, maybe later on also I will give you a reminder of this. Bode plot actually is not just meant to serve as a refresher of whatever we already know, or just a way of defining certain terms like resonant frequency. Independent of root locus, Bode plot is supposed to allow us to design lag lead compensators just like we did using root locus, okay, independent. So this time domain control strategy or control design like root locus and this frequency domain control schemes like Bode plots, they are supposed to run independent of one another and they are supposed to give us equally good performances, okay. Similarly, by frequency domain characteristics, we should also be able to specify performance metrics. So things like bandwidth, things like phase margin, things like resonant peak, yeah, all of these actually do specify the performance metrics of the system in frequency domain, just like rise time, peak time, settling time, percentage overshoot did it in the time domain. Okay. So at this juncture we will not actually get into I mean not just at this juncture, at any point we will not really try to cook up a parallel design technique or synthesis technique, because there are a lot of other interesting topics that we might then miss, right. So I will just say that once we have covered Bode plots, which will still probably take a couple of lectures or more, yeah, we will not cover detailed compensator or controller design using Bode plots, although it can be done, yeah. But once we are through with Bode plot, you will be equipped with all the tools that are necessary to read up this controller design or compensator design techniques given in standard textbooks on your own. So please do that and see that you are in a position to view a compensator design or a controller design technique in the frequency domain independent of the technique that you have learned using root locus, that is a time domain technique. Okay. Okay. So enough said, that is kind of like a point that I wanted to put across. So let us now focus on one block at a time, block by block. Okay. So how about this block? It's really quite straightforward. So you draw this, this is 20 log of k, and this is basically phi of omega for g j omega is equal to k, yeah. So remember, this is the same axis, this is the omega axis, one is on the same graph paper where the y axis is linear and the x axis is logarithmic. So log scale, so this is 1, this is 10, henceforth I will just write this on the lower axis, and I will expect you to assume that the upper axis also has the same, yeah. That is exactly what we do in a Bode plot. Whatever is the axis here, axis marker here is the same axis marker on the upper plot. So what is this 20 log k? After all, this is just a static block, it is uninteresting, it is boring, yeah. It does not change with frequency, so it is a constant. So suppose I know that 20 log k is some constant alpha, then I better mark out this alpha here and draw a parallel line, a parallel horizontal line, yeah. So that is my magnitude plot. What about my phase plot? After all, k is a real number. So what is the argument of a real number? Argument of k is 0 degrees. So therefore let me mark out this 0 degree here and draw another flat line, and I am done. Quite simply, that is it. Nothing more needs to be done about this, yeah. So let us then move over to the next block. The first block was pretty uninteresting that way. So next block is j omega to the r, yeah. So let us try to figure out. So now we are going to plot this again, as I said before. I am going to now just, so I am going to start a little lower on the scale. This is 0. Instead of starting from 0.1, I am now starting from 0.01. So this, as I said, is 1 decade. Remember, this is 1 decade. 1 decade. This is also 1 decade. This is also 1 decade. Yeah, as we say, 10 years is a decade, no, in time. So here, basically, a 10 times multiplication of this frequency is a decade on this scale. So this is 1. This is 10. This is 100, this is 1000, and of course those same points, I am not going to write those labels again, those axis labels, you can easily see that they are going to be the same, yeah. So this is 20 log m, and this is phi. This is the 20 log m axis, and this is the phi. Okay. So now the next block we are considering is g j omega is equal to j omega to the power plus minus 1. So immediately you see 20 log m omega at omega is equal to 1 is nothing but 0, yeah. So let me mark out this 0 dB line here, this is the 0 dB. So So this 0 dB line is here and this is 1. So this is one point that I am readily able to evaluate. Yeah. So let me do that. Now what happens when this is 10? Yeah. What happens when omega is 10? Now you pass it through this logarithm here, this becomes 20 log 10 to the base 10. So this is just 1. So this goes to plus 20. Yeah. So let me mark out this 20 here, this 40 here, this 60 here, and in a moment it will be clear why I am marking these spaced at 20. And let me mark out this, similarly this is a minus 20 here, let us say this is minus 40 here, this is minus 60 here, okay. These are all in dB. So now notice that I know that this curve passes through this point. So let me check out at 10. So at 10 this is equal to 20. So at 10 it is going to be 20. What about at 100? Yeah, another decade ahead. So this is at 100, 20 log 100 to the base 10. Yeah, this is 40. So you can check that it will keep growing like this. So this is growing at as if plus 20 dB per decade. Yeah. So this fellow passes through 0 dB at omega is equal to 1 and then rises at 20 dB per decade if this sign is plus here. By the same token, so let me just join this line here, this is just going to be a straight line plot. Sorry if this is not matching, it's just my bad drawing. Yeah. So this is going to sort of 60 is going to be at 1000. Yeah. So this is a straight line, even if it does not look, because again of my pathetic drawing, it is a straight line rising at plus 20 dB per decade, and therefore it makes sense that it will go on like this. Yeah, it is a constant straight line at 20 dB per decade. Similarly, if you take this minus sign here, that will also pass through this, just the only difference being that it will now pass through, and this slope will be, so this is for j omega to the power minus 1, that is a pole at the origin, and this is for j omega to the power plus 1, that is a 0 at the origin. Yeah. So this one will go at again a straight line with a slope minus 20 dB per decade. So that is it, that is all there is to this magnitude plot, right. And that is all there is to this magnitude plot. I need worry about nothing more beyond this. What about the phase plot? Look, what about this phase plot? This is either a purely real number or a purely imaginary number, depending on what power you raise it to. Of course, for plus minus 1 it is going to be purely imaginary. Yeah. So if it is plus 1, it is going to be 90 degrees, if it is minus 1 it is going to be minus 90 degrees, if it is plus 2 it is going to be 180 degrees, because it is then minus omega squared. If it is minus 2, yeah, it is again going to be, whether you call it minus 180 or plus 180, it does not matter, but yeah, just for the convention's sake. Yeah. So maybe I will just call this 90 degrees here and this as minus 90 degrees here. So let me draw with the green line corresponding to plus 1. So this is the plus sign, and the red line corresponds, sorry, I think I should write this in green then. Yeah. So this is j omega to the power plus 1. So this is plus, and the minus 1, let me write it in, let me draw that in red, sorry. So let me draw that in red. Yeah. So here also you see this is the line corresponding to j omega to the power minus 1, and this is the line corresponding to j omega to the power plus 1. So immediately, almost in no time, we have actually figured out how to draw two of these blocks. Yeah. So we figured out, so if you are given now just a transfer function of a system with just poles and zeros at the origin, you will now be able to cook them up. How? Just add up these individual plots. At every point you just add them up, yeah, and you can always add up two curves. After all, what are these curves? These are just straight lines, yeah, either with a constant slope or flat lines for the phase, yeah. So it's very easy. So in other words, if the DC gain is increased, you can immediately see that the overall Bode plot will rise. If the DC gain is decreased, the overall Bode plot falls. Later on we shall see some outcomes of these, and we shall see there is a way to interpret this as a stability, insofar as stability is concerned, there is a way to interpret all of these consequences. Okay. So already almost in no time we have seen two of these blocks. One is this constant block K, the other is this pole or 0 at the origin. The next block that we are going to look at is 1 plus j omega tau to the power plus minus 1. And here is what we are going to do some approximations. Now the more perceptive or the more fastidious of you might not be very happy with these approximations, these asymptotic approximations, but I assure you that the benefit that is to be had from getting an exact root locus plot as opposed to the asymptotic root locus plot is way greater than the benefit that is to be had from really getting a more accurate Bode plot rather than just the asymptotic plot. In other words, what I am saying is, even though I myself insisted on going through with many of these fine tuning techniques while drawing root locus, I would say that while drawing a Bode plot, it is not really that important to get these errors corrected and to bend around these so called corners, as we shall see, and yeah, and to correct this plot at certain special chosen frequencies, because there is no limit to this rigor of correcting this plot. After all, it is just a plot. So we shall see in general that ultimately at the end of the day, the asymptotic Bode plot gives us a lot of information, in fact most of the important information to a fair degree of accuracy. So it is not like you are going to lose out on a lot of information by not drawing the accurate Bode plot as opposed to the asymptotic one. So therefore, we shall mostly concern ourselves with the drawing of the asymptotic ones, except for some very few points, maybe the break points or the so called corner frequencies. I will really not insist on making corrections. You will see in many textbooks they have pages after pages of several plots and tabulated data, yeah, giving you how exactly this Bode plot varies as omega changes. But for my, as far as I am concerned, I would say that, well, it suffices to just draw the asymptotic plot, particularly since we are not really going to use Bode plots for precise controller design, yeah. Rather we are going to look at Bode plot as an analysis tool. For that same reason, I am not really too insistent on making these fine corrections. In fact, even as far as these corrections go, not all textbooks actually are in agreement as to what kind of corrections are to be made and where you are going to approximate the asymptotes from. We shall see that by and by. Right now it might appear like very cryptic whatever I am saying, but as we see all of these blocks that we are we have set our goals to, yeah, as we see each of these blocks how they look, we will eventually see that these corrections, how they come about, and how getting too much into this correction business actually takes the flavor away from this Bode plot and makes it a very sort of a nasty kind of calculations at the end, yeah. So let us look at this particular type of block, and we will end here today. So maybe in the next lecture we shall focus our attention on this blocks of the second order kind, yeah. So today we will set our goals to end this lecture by looking at blocks of this form. Okay, so as always, let us draw this again. Sorry, this is too bad even by my appalling standards of drawing. Okay, so this is omega, the independent variable. This is 20 log to the base 10 m, yeah. So again you have 0 dB. So this is all in dB. I am not writing the units. This is 0, this is 20, this is 40. Sorry, yeah, this is 40. Yeah, this is 60, and then 80, and so on. And this is minus 20, minus 40, let us say this is minus 60, minus 80, so on and so forth. Now, in order to draw for this, we will consider 3 different cases. 2 of them will be asymptotes and 1 will be an exact value. Okay. So, you notice that as omega tau is much less than unity, yeah, m omega is close to 1. Therefore, 20 log m omega, yeah, is almost 0, yeah, and based on this we shall draw our so called low frequency asymptote, which is just a flat line at 0 dB, yeah. Similarly, if you now look at phi, the phase function, phi omega also tends to 0 degrees, is it not? So, let us say this is a 0 degree line, yeah. So, again phi omega also we draw this 0 degree line, right. Okay, we are good to go. Now, for omega tau much greater than unity, you see we can drop off this 1. So, this will resemble the plot for this pure integrator or this pure differentiator, yeah. So, therefore, that high frequency asymptote, so let me now mark out this. So, this is 0.01, this is let us say 0.1, this is 1, this is 10, this is 100, this is 1000, okay. So, this, same points here, I am not rewriting them as I said earlier. So, what about the high frequency asymptotes? So, the plus 1, again let me denote by the same symbol. So, this plus is by the green and the minus is by the red, okay. So, now what is my high frequency asymptote? So, in other words, this condition, note that this condition is the same as saying that omega is much less than 1 by tau, and this condition is the same as saying that omega is much greater than 1 by tau. So, this 1 by tau is the so called corner frequency or break frequency, okay. All right. So, let me just say that this is scaled by omega tau, it is just a scaling factor, no, it does not matter, okay. So, suppose I take this plot as omega tau itself, I am not just going for omega, I am going for omega tau. So, now notice that as omega tau is equal to 1, or rather omega tau is much greater than 1, this is another asymptote which looks like this. So, this is going to be 20 dB at here and 40 dB out here, okay, maybe this is not a very well drawn asymptote, I should erase this. So, let me be a little careful about this. So, this is 20 dB here, this is 40 dB here, this is 60 dB here. So, basically at omega tau is equal to 1, it must be here, at omega tau is equal to 10, it must be here, at omega tau is equal to 100, it must be here, that is enough. So, that is my high frequency asymptote, yeah. And similarly this is for r is equal to, this is for plus 1. So, this goes at 20 dB per decade, plus 20 dB per decade, the high frequency asymptote corresponding to this case. And similarly, when it is minus 1, this is going to be minus 20 dB per decade, that is here, then we are going to be minus 40 dB per decade, that is here, and minus 60 dB per decade, that is here. So, let me just join those dots as best as I can with a straight line. Again, excuse my bad drawing, but this is supposed to be a straight line, and this is falling at minus 20 dB per decade, just like just like I had this line, yeah. And now let me draw in bold the low frequency asymptote. So it turns out that the low frequency and the high frequency asymptotes meet at omega tau is equal to 1. So of course you can drop off this tau, yeah, and you can scale this at 1 by tau. So instead of this, if you want to scale this at omega, if you want to have your independent axis as omega, then divide all of this by tau. I have just chosen the axis to be omega tau, it really does not matter. I can just choose this 0.01 by tau, this 0.1 by tau, this 1 by tau, this 10 by tau, this 100 by tau, so on and so forth. Yeah, does not really matter. Okay, now this part is at least done, but what about at omega tau is equal to 1? And this is where we can introduce some correction. You will see that this m omega is equal to square root of 2. So therefore 20 log to the base 10 m omega is equal to approximately 3 dB. Why am I saying that? Because log 2 up to the base 10 I know is 0.3, yeah, so because of the square root half will go out, so it will be 10 log 2. So 10 times 0.3 is around 3 dB. So basically if you are now very finicky about making a correction here, then you can make a 3 dB correction here for the +1 case. So maybe you draw the +1 case instead of drawing this asymptote. If you are very perturbed by the fact that this is joining here at a very sharp corner and you do not want those sharp corners, that is what I said, bending around the corners, right. And similarly in the lower asymptote, in the case of -1, so this is the -1 case where this exponent is -1, yeah, you can make this correction here and you can join this line here like this, yeah. So that is going to be a reasonably accurate sketch, but as I said, we will not bother about all of this, we can just take this asymptote and we will be happy with it. Next, we are not yet done until we have seen what happens to this phase plot. Now unfortunately in the phase plot, unlike in the magnitude plot where you see the low frequency asymptote and the high frequency asymptotes, they intersect at a point. So even though it might not be differentiable at that point because of the bending around because of the corner, the sharp corner, but at least it is continuous. Now unfortunately in the frequency, in this case, you see here this is 0 degree, and if you look at this here, it is going to be phi omega is going to be plus minus 90 degrees, yeah. So basically your high frequency asymptote is going to be like at -90 like this, so this is -90 and here you have a plus 90 degrees, yeah, so this is a plus 90. So what do you do, yeah, so your low frequency asymptote carries you all the way up until here at 0 degree by this, and then your high frequency asymptote takes over and you find that there is a jump discontinuity here. So of course I personally do not mind if you just join it by a vertical line like this, yeah, it really does not matter much, okay, that if you join it like this, but so some textbooks actually do that, they just plot the asymptotic version. But if you want to join it out smoothly, there are two different ways that different textbooks adopt. In some textbooks they will just go 1 decade below and 1 decade above, yeah, and they will not continue with this asymptote all the way up until the break frequency. So what they will do is they will just join this point with this point. So you just join. So overall plot for +1 will then look something like this, and overall plot for -1, sorry I should have drawn this with a green. So overall plot for +1 will look like this, and overall plot for -1 they make it appear like this, yeah. So that is one approximation of the asymptotes to make it appear continuous. And then some people will insist that we also want to bend around these corners and smoothen it out, but again really not a big deal, yeah. Some other textbooks would also suggest that don't go all the way up all the way down to 1 decade and all the way up 1 decade. Why don't you just go half a decade, or rather 1/5 rather than 1/10 all the way down, go 1/5 of the way down and go 1/5 of the way up and then join these points, yeah. It is just a matter of which approximation, whatever floats your boat, yeah. At the end of the day the asymptotes do not intersect in case of the phase plot, yeah, that is all that concerns me. So there is a discontinuity, You can draw the discontinuous asymptote like I showed earlier, that is a valid way of drawing the asymptotic Bode plot. Otherwise, if you are unhappy with the discontinuity, you can make any one of these two approximations, either go 1 decade below and 1 decade above. 1 decade above you pick the high frequency asymptote, 1 decade below you pick the low frequency asymptote and join those 2 points, or go half a decade below, that is 1/5 of the way down, and half a decade above, go 1/5 of the way up, and again join the high frequency asymptote from 1/5 of the way up to the low frequency asymptote 1/5 of the way down. Yeah, at the end of the day, it's just an approximation. So unfortunately, this is all we will have to say about this. We will not really get into the business of nitpicking and correcting all of this, but in the next lecture we will look at second order blocks, which will thankfully turn out to be much more interesting because we have that additional parameter called zeta to still play around with. So more on that in the next lecture. Until then, take care. Thank you.